Cats are amazing acrobats. They have an ability to land on their feet no matter how they're dropped. They achieve this by manipulating the rotation of the front and back of their bodies separately. Today, I'm going to do an experiment to test that ability, and maybe learn some basic statistics along the way. This is our cat, Mr. Green Jeans. Today we're going to find out if Mr. Green Jeans is a cathlete. We're going to use this setup to see just how good Mr. Green Jeans is at landing on his feet. Okay, let's go get the cat. Come here, Mr. Green Jeans. That's a good kitty. Now come on. Let's go. Well, that didn't work. Let's try something else. You might already be aware of the idea that when toast is dropped, it tends to land with the butter side down. Usually. It turns out that there are good scientific reasons for that. This paper, published in the European Journal of Physics, predicts the behavior of a piece of toast falling off of a table. It even has equations predicting the rotation of the toast, and these equations explain why we expect toast falling off of a table to rotate exactly 1/2 times and fall butter side down. Conveniently, this phenomenon was already investigated by the Mythbusters. Adam built an automated toast flipper. By labeling the top and bottom of the toast, with the top being the buttered side, he discovered that, as predicted by the physics article, toast does indeed generally flip a 1/2 time and land buttered side down on the floor. Perhaps more interesting, though, is the follow-up experiment where the Mythbusters decided to drop toast from a vertical position off of a roof. This is because the theory of toast flipping onto the butter side relies entirely on the human behavior of putting toast on the edge of a table and knocking it off. In other words, it has nothing to do with the toast itself. But what happens if we eliminate the human component?
What's the breakdown so far?
Out of 17 drops, the butter has landed up 12 times.
So butter up is winning.
Looking at the Mythbusters data as a whole, we see that the bread landed butter side up 29 times and butter side down only 19 times. Why did this happen? Well, of course, the Mythbusters have a theory.
Adam, I actually saw what was going on here. The ones that were landing butter side up were ones that had been kind of pressed in a little bit because it forms a dish in the bread. And just like a leaf coming off a tree, if it comes off neutral and it's curved, it doesn't want to float down like this. It wants to go like that.
I totally agree with that assessment. I saw the same thing from up there.
But how do we know if Jamie's theory is even necessary? In other words, is this result really remarkable? Is it any different than what we would expect if the toast just randomly landed on one side or the other? To find that out, we can use a variety of statistical techniques. The rest of this lecture will discuss those techniques and how they can be applied to this problem and to statistical inference in general. This is Lecture 2, Fitting Statistical Models to Data. Before we begin, I want to show this general overview of a statistical test that shows the basic workflow going from a data set and a null hypothesis to a p-value. A lot of statistical tests, like ANOVAs and t-tests, fit into this framework. A lot of things that we'll do in comparative methods, like tests using independent contrasts or phylogenetic ANOVAs. We'll walk through this framework in general using our toast example, and then we'll come back to it with later examples from comparative methods throughout the course. We begin in the upper left corner of that blue box, which represents our data set. The first step in doing our statistical test is to measure that data set, to summarize it in some way. We call the thing that we use to summarize our data set a test statistic. The test statistic is our attempt to get the information relevant to our hypothesis out of our data. If we're thinking about whether our toast is fair or not, we can use a very simple test statistic which is just the number of times that the toast came down butter side up, which is 29. Out of our 48 trials, butter side up 29 times, butter side down 19 times. So we have our data set and we have our test statistic, which measures our data set, but now we need to think about our null model. What the null model represents is the simplest possible explanation for our data. We try to pick a null model that doesn't have any of the biological processes of interest. For example, in our toast flipping question, we were asking whether the toast comes up butter side up or butter side down more frequently than we expect by chance. To imagine a world called null hypothesis world. Null hypothesis world is a world where nothing interesting ever happens. For example, toast that lands on one side more often than the other is kind of interesting. Too interesting for null hypothesis world. On null hypothesis world, if you have a piece of toast and you drop it, it's equally likely to land butter side up and butter side down, no matter what. Imagine collecting data sets like what Mythbusters collected on null hypothesis world. How would you do that? Well, you would have to flip toast. We could use the same robots, even the same buildings, and we would want to flip that toast the same number of times that was done in the experiment. What I want you to think about is, what would your data look like if it was collected on null hypothesis world? So maybe you did 48 flips and the toast came out butter side up 26 times. Well, that's still not enough to tell us really much about our data. Our data landed butter side up more often than that, but there's only one trial in each time. So we could repeat our experiment again in null hypothesis world, obtain a result of 21, 24, 23. If we redid this experiment over and over again, we would get a slightly different result every time. If you imagine doing this experiment over and over and over again, you could get a whole distribution of the number of times the toast lands butter side up. It turns out that we can mathematically figure out what we would expect this distribution to look like on null hypothesis world. It's a binomial distribution. And here's a picture of what a binomial distribution looks like in this case for 48 trials. So that distribution captures what we would expect to happen on null hypothesis world. If the data looks like it could have been generated on the null hypothesis world, then we fail to reject the null hypothesis. If, on the other hand, the data looks unlikely to have been generated on null hypothesis world, then we reject the null hypothesis. Actually, maybe given the state of scientific publication, I should reverse those cats. The next step is to compare the test statistic from our data set to the test statistic that we would expect on our null planet under the null hypothesis. That's where we obtain our p-value, and the p-value is the summary of the result of our frequentist statistical test. To understand how to calculate a p-value, let's go back to our binomial distribution of expected outcomes on the null planet. This time I've marked that binomial distribution with our result from the real data, which is 29 times that the toast came butter side up. So is this an interesting result? Is this likely to have happened on our null planet or not? Well, you can kind of eyeball this result and see that it's not that far out in the tail, but let's try to quantify that with a p-value. One thing that you might think of doing is to calculate the exact probability of obtaining this result under the null hypothesis. We can just read that off from our chart as being about 0.04. However, what we really want to calculate with our p-value is the probability of obtaining a result that is equally or more extreme than our observed value. That means we want to calculate the probability of getting a result that's at least 29 times butter side up or even higher, which is represented by the area of the histogram that's greater than or equal to 29, those yellow bars right there. In this case, we want to calculate a two-sided p-value, meaning that we want to consider extreme results on the other tail of the distribution. So we should also mark the left tail of our distribution in yellow. And if we calculate the total area of those two yellow tails, we see that the p-value from this test is 0.19. If our p-value is less than 0.05, we reject the null hypothesis, but our p-value here is greater than 0.05, so we fail to reject the null hypothesis. What does this mean? What it means is that the Mythbusters didn't need any special explanation for their data. The result that they obtained is likely to have occurred even if the toast was equally likely to fall on either side, butter side up or butter side down. So they don't need any kind of complicated explanations that require the toast to fall like a leaf or anything like that. What they do need is statistics. What I hope this example illustrates is two things. One, that statistics are good at helping us see whether there's something interesting in our data or not. Humans have a tendency to apply elaborate explanations to things when they might not be needed. Second, that we can understand the frequentist statistical design with this simple diagram, thinking about our data, test statistics, and null hypotheses. But this frequentist design, and especially the focus on p-value, has some severe limitations, and many of those limitations can be overcome in other frameworks like maximum likelihood or Bayesian inference. So let's go into those other two topics for the rest of this lecture. So let's talk about likelihood. Likelihood is defined as the probability of obtaining your data given a model and parameter values. We can write that in equation form as the likelihood of your hypothesis given the data is the probability of obtaining your data set given your hypothesis of interest. The simplest way to illustrate this is by going back to our example. Imagine that we have some model of how that toast might be flipped. We want to calculate the likelihood of that model. To calculate that probability value, we just need to think about the probability of getting the particular data set that we have. Say that we flipped the toast n times, and of those n flips, we have k times that the toast was butter side up. And we denote the probability of obtaining a butter side up flip as p. I'm going to use some kind of weird terminology here, but it is meant to tie what I'm saying to the statistics literature. So I'm going to start calling butter side up flips successes and butter side down flips as failures. That might seem a little strange, and it's arbitrary. In fact, we could call butter side down flips successes also, and everything would still work. But all the statistics terminology for this talks about successes and failures, so that's what I'm going to say. Well, the probability of obtaining k butter side up flips is p to the power of k. That's our k successes out of n trials. We also then have n minus k failures, each with probability 1 minus p. So we can write that down as part of our equation. The probability listed there is the probability of obtaining any particular sequence of k successes and n minus k failures. If we want to account for any sequence that has k successes in it, we just need to add this term out to the beginning, which is n choose k. That formula right there then gives the likelihood of our hypothesis given the data, which is the probability of getting our data set given the hypothesis that we have chosen. This formula, incidentally, also gives you the binomial distribution that we've been using in the other examples through this lecture. One of the things we can do in our likelihood equation is change the model. And in this case, we can change our p parameter, which gives the probability of obtaining a butter side up flip. For example, when p equals 0.5, we have a fair toast at the top. We have our binomial distribution centered around 24. If we change the model so that p is 0.6, that is, there's a 60% chance of obtaining a butter side up flip, then you can see that distribution shifts to the right. We can also look at where the likelihood of our particular data set would be. Remember, we had 29 butter side up flips. And we can see that the probability of obtaining that outcome differs dramatically between our two different models. If we look at how the likelihood depends on our model parameter, the likelihood has a peak at around 0.6. That's the maximum likelihood estimate for that parameter p. So this is one way to estimate our model parameter, just by calculating the likelihood of different values of p, and then finding the value of p that maximizes that likelihood, that gives us the highest chance of obtaining our data set given our model. Sometimes we can even do this analytically without having to calculate thousands of likelihood scores. We can also put this in a model testing framework by using a technique called the likelihood ratio test. In a likelihood ratio test, we compare the likelihood of a simple model with a more complex model. We can then compare the likelihoods of these two different models using a likelihood ratio test. So, for example, is our toast fair? Well, we have our simple model, which is a fair toast, and our fair toast has a probability of landing butter side up 50%, 0.5. This is what we were using as our null model before. Our more complicated model is a biased toast, where it has some unknown probability of landing butter side up, which is estimated using maximum likelihood. And these are the two models that we're going to compare using our likelihood ratio test. We will call the likelihood of our first model L1, and our second model is L2. So we have our likelihood formula from before. We can calculate the likelihood of our first model as 48 choose 29 times 0.5 to the power of 29 times 1 minus 0.5 to the power of 48 minus 29. That's our 29 butter side ups and our 19 butter side downs. And we get a likelihood of 0.041. For model 2, we change the p and the 1 minus p term in that equation, and we get a likelihood of 0.117. Notice that the likelihood for our second model is higher than our first. That's because we're using the maximum likelihood parameter value, which is the parameter value that maximizes that likelihood term. The next step is to calculate a test statistic, which is 2 times the log ratio of L2 divided by L1, or 2 times the difference between the log of likelihood 2 and the log of likelihood 1. Substituting in our values, we obtain a value for delta of 1.05. Now we need to calculate a p-value. To calculate a p-value, we compare delta to a chi-squared distribution. Chi-squared distributions have different degrees of freedom, so the degrees of freedom in the likelihood ratio test is the difference in the number of parameters between the two models. When calculating parameters here, we only want to count free parameters, that is, parameters that we're using the data to estimate. We don't want to count any parameters that are fixed, for example, the n value of 48 toast drop. If we look at our two models and ask how many free parameters they have, in our simpler model, we've set the model parameter to be 0.5, and so there's no free parameters in that model. In a more complex model, we estimate p, that's one parameter, and so the two models differ by one free parameter. A chi-squared distribution with 1 degree of freedom looks like this. We can find our value of delta on this distribution. What we want to do is find the area of the distribution that is equal to or more extreme compared to our test statistic. For chi-squared distributions, only high values count, so you want to just use a one-tailed p-value and not consider both tails, and obtain a p-value of 0.31. This p-value is greater than 0.05. We fail to reject the null hypothesis. You might realize at this point that what we've done for a likelihood ratio test is exactly the same as what we did in our previous discussion of frequentist hypothesis. We had a data set, we calculated a test statistic, in this case delta, and then we compared that test statistic to what we would expect under our null model, which is actually a chi-squared distribution with 1 degree of freedom in this case, but that really comes from what we would expect if our simpler model with a p fixed to 0.5 were the truth. In other words, we're back on the null planet. Likelihood ratio tests are good when you have two models and one is a special case of the other. But in general with likelihoods, you can compare models in a more flexible way using the Akaike information criterion. AIC is a simpler and more flexible way to select models in a likelihood framework. To use AIC, we use this equation, AIC equals 2k minus 2 log likelihoods, where k is the number of parameters in the model and L is the likelihood. We can then select the model with the smallest AIC as our preferred model. For the example that we're considering here, for model 1, we can plug in the number of parameters and the likelihood. In this case, we have 0 free parameters and the likelihood of 0.041, and so an AIC score of 6.39. We can calculate AIC scores for our two models. For model 1, we have 0 free parameters and a likelihood of 0.041 for an AIC score of 6.39. For model 2, we have 1 free parameter and a likelihood of 0.117 for an AIC score of 6.29. The AIC score for model 2 is slightly lower than the AIC score for model 1, so we should show a slight preference for that model. However, most researchers would not reject model 1 in favor of model 2 in this case because the AIC scores are so close. In fact, in order to really favor one model over the other, we should look for differences in AIC scores of 4 or more. In conclusion, maximum likelihood is a really nice way to estimate model parameters and to compare the fit of different models using techniques like likelihood ratio tests or AIC scores. Next, we'll talk about Bayesian statistical inference, which is a different statistical framework that gives us a lot more flexibility in quantifying the uncertainty of our models and parameter estimates.